In previous video, we talked about features. What are features? In this video, we are going to talk about regression problem. What do we mean by regression? First of all, it's a supervised learning. It appears in supervised learning. Supervised. What do we mean by supervised learning? As I told you earlier, we have some set of attributes, maybe features, feature 1, feature 2, feature 3, and maybe several features, feature D, let's say we have D features. And then we have a target, let's say this target, Y. And we want to learn a mapping from these features to this target, If this target, or I'm not calling it as a label because label is label is more specific to classification, because when we talk about label, we think about some finite categories and stuff like so. I'm calling it as a target. If this target is some continuous value, it is not a categorical attribute, let's say. It is some continuous. For example, if we want to predict, let's say y is the price of a house, and these are so many features that represent, for example, f1 is the total area, f2 is the location at which the house is located, f3 is the total number of rooms and all that. If all these are features, then y might be a price of the house, or the sale price of the house. If you want to sell it, what will be the price? Now this y is no longer a categorical. I mean, these are not just some set of categories in which the y falls. Y can take any continuous value. It can have any price. So the supervised learning problems in which your target is not categorical but rather a continuous value, that generally is called regression. And the target may not be just a single value. You may have multiple targets, for example y1, y2, y3, maybe for example y1, y2, y3. You may have multiple targets. You may want to predict those. Just to convince you about the multiple targets, let me go back to give you example of a regression data set that I showed you earlier. Here we are interested in two targets. One target is next temperature maximum, the maximum temperature on the next day, and another target is minimum temperature on the next day. So these are two targets. We might be interested in the two targets, or maybe we are interested just in one target. Maybe we are interested in just the maximum temperature in the next day and stuff like so. But because the temperature can take any value, like here it can be 29.1, 30.5, 31.1 and so on. It can take any value. These are not categories, these are not classes. That's why this kind of data is called regression data, and the kind of problem we will be able to solve using it is called regression. So let me go to Jupyter Notebook and give you in the next video and give you some look and feel of regression by doing some code on a synthetic data set, for example. So hope to see you in the next video. Okay, in the last video I discussed regression, the problem formulation. What do we mean by regression? In this particular video, I will be showing you some plots to get a better look and feel of what do we mean by regression. Because we are going to do some visualizations, I will not be considering a lot of features. Primarily, I will be considering just one feature. So let's say we have a lot of samples and each sample is available with just one feature. And then we have some target that we want to find out. and we want to find out a mapping between the feature and the target. But because I'm going to show you just a toy example with just one feature, but the concept is basically generalizable to several dimensions. Although the visualizations in visualization with several features is not always easy, sometimes impossible. So let me just show you some example of a data set that we generate ourselves, and then we try to actually predict what is happening. Let me show you a regression example here in Python. So let's say we generate some data point. Let's say we have total number of data points. Let's say we have 20. Let's say these are the data points we have. Let's say X, capital X. Throughout in this course, we will be using capital X as data and small y as targets in supervised learning. And wherever we use unsupervised learning or clustering, we will be using capital X for data, because y will not be available there. So let's say np dot range. Let's generate some points, np dot range n. And let's say the actual mapping between x and y is just a line, let's say, or maybe some function. Let's say 4 is static capital X plus 3 is static. This static means multiplication. So let's say that x is related by y in a following way. X square. Let's say this is some and minus, let's say 100. Let's say that's a mapping between x and y. Let's say y depends upon x in such a way that if you multiply the value of the feature, the only one feature, with 4, and then you square the feature, you take the square of the feature, and then you multiply that with 3, and then you subtract 100 from there, then you reach the target. Let's say that's the scenario. So if this is the scenario, let's see what is the actual pattern between x and y. Let's see a scatter plot. Yeah. So this is what, let's say this is the mapping, so between x and y. Let's say this is x-axis, which is feature value. So these are the feature values, and against each feature value, that's what our prediction is. What will happen in reality is we will be just available with x. So we'll be available with x, and we will be available with y, the corresponding targets. What we do not know is the mapping between x and y. So this function that maps from x to y, that is unknown. Because we will be just available with data, the recordings, we do not know what is the mapping between x and y. What kind of function, what kind of mapping exists between x and y. And the task of regression here is to actually learn that mapping. Use this data, use the available data. So given a lot of x and y, you may come up with that actual mapping that is hidden inside. So let's try to find out that mapping. Here, for example, in this example, I'll be using a built-in function from scikit-learn for regression. Although later in the course we will actually code linear regression from scratch, and I will explain the underlying theory of regression, how actually these functions they work. But right now, I'm just to give you a look and feel. Let me just think that. Let me just use the scikit-learn model to get a linear regression model. So let's say from sklearn dot linear model, import linear regression. You might be thinking, why linear? Why you are importing linear model? Because the relationship between x and y is not linear. I mean, that is not a linear model. So why you are importing linear model? Hold on. Actually, this linear model is capable of, that's a general linear regression model, that's a general model, and it is capable of actually, although the name is linear, but there are ways to extend that for non-linearities as well. But let's just fit a linear function. Let's just, we have data, we have x, the corresponding y's. Let's just try to predict a function, try to predict a mapping that maps from x to y. So let's see. Let's say we build a model. Later in this course, I will explain what a model is, but let's just bear with me. Let's build a model, linear regression. Let's say that's a model. Model dot fit x, and here x is just one dimensional, only one feature, so it's an array with just one axis. So new axis, and the scikit-learn or this scikit-learn package, it actually requires the data in 2 dimensions. So this basically, this np.new axis, just add a dummy axis to your data, and then the data just becomes consistent with scikit-learn. Then what we do is we predict. Now we predict, because now we have model M. Let's predict the y values. Let's say we have a mapping now, m dot predict x np dot new axis. So now this m is basically that mapping that somehow we learned. Later in the course, I will show you how this learning actually happens. But right now, this fit function, I'm not showing you the implementation of this function right now. But there are some ways with which you can actually learn the mapping. Let's see how well we learned the mapping. Let's see. So let's plt dot scatter. Again, let's plot the original data, and let's plot as a solid line of what we have just predicted. And let's take the color as red. So there will be a red line that will be showing the pattern, that the mapping that we get, and the blue dots, they will be showing the actual data that I've shown you earlier as well. So if there is no bug in the code, it should run and should display some plots. Yeah. So this is what we come up with. Basically, our model is showing us that on this particular value of x, the y value is just this much to the red line, but the actual y is this. So it is making some errors. Fine. But mostly, if you see in this particular region, the error is so small. So that's what the pattern that we got actually. Because we do not know the actual mapping between x and y, what kind of actual mapping is there. So we started with just fitting a line. We might have started with something else. Maybe right now, if you're getting an error, that we are just visualizing the error. Later on, we will see how can we actually have errors. How can we have error matrices, error metric or error measure without actually visualization? What are the ways, or what are the automatic ways to, you see the error and then you adopt the model, and then you go and set the model again and stuff like so. But right now we are visualizing that there is some error in this particular case. So maybe we think that let's allow the model to not stay linear. Let's allow the model to become a little flexible. So if you restrict the model to stay aligned, there is no way that a line can fit all this data very well, because the data itself does not lie on a line. So let's allow our model to be some flexible. Let's allow our model to be a 2-degree polynomial. And let's say then how it works. So let me just copy this code again. Let me just copy this code and paste down in another cell, just to show you how can we fit a 2-degree polynomial if we really want, because the actual mapping is 2-degree polynomial. So let us see how can we do that. So now, for example, here, So we just, let's say, import the polynomial features from, let's say, from scikit-learn dot pre-processing import polynomial features. Yeah, so let's import those. Why will this be working? What are polynomial features? Hold on, I'm just giving you here an example just to get you a look and feel, a better look and feel of regression. Later on, I will explain what do we mean by polynomial features and how this linear regression model can be used to fit arbitrary kind of polynomials. And even I will explain what a polynomial really is. But right now, I'm going to fit a 2-degree polynomial. I'm trying to do that at least. So what I will do is I will do the following. I will transform my features to the new features. Let's say x poly, new features. And what I will say is x poly is, so first I will define my polynomial function, polynomial model, poly model. That is polynomial features with degree, let's say 2. That's degree 2, or we can set degree equals 2. That's polynomial model. X poly is poly model dot fit transform, and here we give x our original data, but we give x in by adding a new dimension, np dot new x is. So now we have our polynomial features. Next, what we do is, rather than fitting to the original features, we fit the linear model to our polynomial features, which essentially means we are fitting a 2-degree polynomial here, which I'll explain in detail later. And then we basically predict a mapping, and then let's see how that mapping goes. So we have, this is our original data, and this is our original data, and that's what we got as predictions. So, oh, there's an error. Polynomial feature fit transform. I guess I have missed some spellings again. Fit trans, yes, S is not there. So how cool is that? You exactly fit. You fit exact, I mean, no error. You learned the model. You didn't know the model, and you learned the model that actually the pattern of x and y, that is this. Now, even if you have more data, you can call this predict function, and you can predict the y values on the feature x. Consider, for example, more samples for which that were not used in training process. And for those samples, you just want to predict the y value given the x value as a feature. You can now just call the dot predict function, because you have mapping now, and you can predict the y values. And at least this pattern shows that you have done very well. Although there is a problem of doing very well on available training data, we will see that later on, but so far it seems like a great idea to just increase the flexibility of the model, to allow the model to become flexible and adapt to the data, available data, because then the tendency is the flexible model will try to adapt to the data, and we will actually get our patterns back. Let's see the different coefficients. Let's see the model parameters that we got. M dot coefficients. What are the coefficients? So there are 3 coefficients: 0, 4, and 3. And remember, we have coefficients here like the actual model was basically 4 is the coefficient for x, 3 is the coefficient for x square, and then we have 100 there, but it is showing me 0. And I will show you what that means. Actually, I have not included the bias here. If I could have included the bias, let me show. Actually, I'm telling you a lot of terms without explanation, so Don't worry if you're not getting these. I'll explain all these things in the relevant sections when we will derive these kind of stuff in detail. So right now I just want to show you. Now if we see the coefficients, they are still 0 because 0 is the best coefficient. Although if we include this bias terms here, that actually allows the intercept to be learned as well. We will talk about intercepts and biases in detail in the course. But the moral of the story here is as follows. You are given a lot of data. Here I have shown just one-dimensional data, which means just one feature was available. And based on one feature, you want to predict a particular target. You may be available with a lot of features, like we saw in the data for temperature prediction. And with a lot of features, you may be trying to predict one or more targets. Now, the whole goal is to come up with a function, a model that actually maps between x to y. Here, that function is reported here in a fit function, dot fit. All the implementation, all the actually crux and the and interesting work is inside this fit function. The common question or the real question is how this fit function is actually working, how it is finding out the actual pattern, actual mapping between x to y, between features to target. And here I have used the built-in function fit from scikit-learn. I promise I will in the later videos I will actually give you a coding of at least one or two algorithms from scratch, and we will be building our own models, our own dot fit kind of functions ourselves. After building one or two functions, we'll be having a very good look and feel that how things are actually working in this scikit-learn, and then we will be again using built-in libraries. But I will give you a flavor of implementing these kind of mapping functions from scratch in NumPy for a couple of examples later on in this course. So yeah, so I end this video here. In the next video, I'll be talking about classification. So hope to see you in the next video.